Welcome to this video about the divergence operator in vector fields. The divergence is a fundamental concept in vector calculus that measures how much a vector field spreads out or converges at a particular point. It helps us understand the behavior of fields like fluid flow, electric fields, and many other physical phenomena. Before we dive into divergence, let's first understand what a vector field is. A vector field is a function that assigns a vector to each point in space. Think of it like a wind map, where, at each location, we specify both the wind's speed and direction. Mathematically, we can represent a vector field in two dimensions as f equals f sub x times I hat plus f sub y times j hat, where f sub x and f sub y are functions that depend on the coordinates x and y. In 3 dimensions, we add a third component, f equals f sub x times I hat plus f sub y times j hat plus f sub z times k hat. Now, let's introduce the concept of divergence. The divergence of a vector field, denoted as divf or del.f, measures the net flow of the field out of a small region around each point. Mathematically, the divergence uses the del operator, which is represented by this upside-down triangle symbol. The divergence is calculated as the dot product of del with the vector field f. In Cartesian coordinates, for a 3-dimensional vector field, the divergence is calculated as the partial derivative of f sub x with respect to x, plus the partial derivative of f sub y with respect to y, plus the partial derivative of f sub z with respect to z. This formula tells us how much the vector field is spreading out at a particular point. Let's visualize what positive divergence looks like. Imagine a vector field where vectors are pointing outward from a central point, like water spraying from a fountain or air being blown from a fan. At the central point, we'd observe a positive divergence because more flow is leaving this point than entering it. We call such a point a source. If we were to draw a small circle around this point and measure the net flow across this boundary, we'd find more arrows pointing out than in, resulting in a positive flux. Now, let's look at negative divergence. Imagine a vector field where vectors are pointing inward toward a central point, like water draining into a sink or air being sucked into a vacuum cleaner. At the central point, we observe a negative divergence because more flow is entering this point than leaving it. We call such a point a sink. If we draw a small circle around this point and measure the net flow across the boundary, we'd find more arrows pointing in than out, resulting in a negative flux. What about zero divergence? A vector field with zero divergence is called incompressible or solenoidal. In such a field, the amount of flow entering any small region equals the amount leaving it. A common example is a circular or rotational field, like water swirling in a whirlpool or air in a tornado. Notice how the vectors flow around in circles without converging or diverging. In fluid dynamics, an incompressible flow means the fluid density remains constant as it moves. Many real-world flows, such as water in pipes or air at low speeds, can be approximated as incompressible. Now let's work through some examples to better understand how to calculate the divergence. Example 1. Let's find the divergence of the vector field f equals x squared times I hat plus y squared times j hat plus z squared times k hat. Using our divergence formula, we need to calculate the partial derivative of x squared with respect to x, which is 2x, plus the partial derivative of y squared with respect to y, which is 2y, plus the partial derivative of z squared with respect to z, which is 2z. Therefore, the divergence is 2x plus 2y plus 2z, which we can simplify to 2 times x plus y plus z. This result tells us that the divergence varies throughout space and depends on the coordinates. At the origin, where x, y, and z are all 0, the divergence is 0. As we move away from the origin, the divergence increases in the positive octant and decreases in the negative octant. Example 2. Let's find the divergence of the vector field f equals y times I hat minus x times j hat plus z times k hat. Using our divergence formula, the partial derivative of y with respect to x is 0, plus the partial derivative of negative x with respect to y is negative 1, plus the partial derivative of z with respect to z is 1. Therefore, the divergence is 0 plus negative 1 plus 1, which equals 0. This is an example of an incompressible or solenoidal field. The zero divergence indicates that the flow is neither expanding nor contracting. In fact, this vector field represents a helical flow, combining rotation in the xy plane with linear motion in the z direction. Now that we've seen how to calculate divergence, let's discuss some physical interpretations and applications. In fluid dynamics, the divergence of the velocity field tells us about the compressibility of the fluid. Zero divergence means the fluid is incompressible, while non-zero divergence indicates expansion or compression. In electromagnetics, Maxwell's equations connect the divergence of electric and magnetic fields to charge and current distributions. The divergence of the electric field is proportional to the charge density, as stated by Gauss's law. In heat transfer and diffusion processes, the divergence helps describe how heat or particles spread throughout a medium. The divergence is also central to the continuity equation, which is a mathematical statement of conservation laws in physics, such as conservation of mass, energy, or charge. Before we conclude, let's briefly touch upon the divergence theorem, which is one of the most important theorems connecting divergence to practical applications. The divergence theorem, also known as Gauss's theorem, states that the volume integral of the divergence of a vector field equals the surface integral of the vector field over the boundary of the volume. Mathematically, it's written as the triple integral over volume V of the divergence of F equals the double integral over the surface S of F dot NDS, where n is the unit outward normal vector to the surface. This theorem essentially says that the total outgoingness of a vector field in a region equals the net flux across the boundary of that region. It's a powerful tool that allows us to transform volume problems into surface problems, or vice versa. In conclusion, the divergence operator is a powerful tool for analyzing vector fields. It tells us how a field expands or contracts at a point, allowing us to understand flows, fields, and many physical phenomena. Let's recap the key takeaways. 1. Divergence measures the outgoingness of a vector field at a point. 2. Positive divergence indicates a source, negative divergence a sink. 3. Zero divergence means the field is incompressible. 4. The divergence operator is calculated as del.f. 5. The divergence theorem connects volume integrals to surface integrals. Whether you're studying fluid dynamics, electromagnetics, or any field involving vector calculus, understanding divergence will provide you with valuable insights into the behavior of vector fields. Thank you for watching.